Hello, everyone. Welcome back to SAT Math Question of the Day with Professor Emeritus Seth Chaiken and his brother Joel Chaiken. We're here to help you understand how to approach SAT math questions. Seth, your face is a little bit too okay, there you go. Good. Good. Okay, so here we go. This is the last question on our practice test for the SAT, and then we have to move to another practice test. This is a calculated question, the last question, number 37. By now, your brains are completely fried. So it's a little artificial for us to do this nice and calmly. And today's Throwback Thursday, which means we will go back 20 years at the end of this thing. We'll go back 20 years and look at a question from 20 years ago. All right. So it's obviously a word question. Botanist is cultivating a rare species and currently has 3,000 of these plants. Population of species that the botanist expects to grow and next year can be estimated from the number of plants this year by the equation below. This is called a recursion relation. What happens now depends on what happens next year depends on what happens now. It's a lot of things in life are like that. The constant K in this formula is the number of plants the environment is able to support. Okay, this comes from biology type thing. According to the formula, what will be the number of plants 2 years from now if K is 4,000? So this is a recursion. So 2 years from now. So this is now. We have to go 1 year forward, and then we have to go 2 years forward. And this relationship tells us how to get the 1 year. And after we get the 1 year, we plug it back in and we get the 2 year. So year one is equal to this year, which is 3,000.
Yeah, that's
plus,
now.
Yeah, that's now. Yeah, that's the now. Yeah, year one is 3,000. Now I'm trying to be neat. See here? Look at this. Times this year, 3,000 times 1 minus 3,000 divided by 4,000. Can I just write 3/4?
Yeah.
Okay, because we have to, when you're doing the test,
you have to be careful. You have to be careful because next time that 3,000 will be different.
I know. Yeah.
Okay.
We know that. Okay, so yeah, of course, that's the whole point of this problem. You have to be careful because it's a recursion.
Yeah.
So this is 3,000. Now, oh, by the way, this calculator. Okay, calculator. Where's my calculator? Because we want to get this done. Oh, God. Yeah. I hope this doesn't happen on your test. You got to keep the calculator near you so you know where it is. Okay, so 1 minus 3/4 is a quarter. So it's a quarter times 3,000 times 0.2 plus 3,000. Okay, 3,150. That's year one. Now, year one goes in as this year again. So year two is equal to 3,150 plus 0.2 times 3,150 times 1 minus. Now, this really is a calculated question. Come on. This really is a calculated question. Wow.
Yeah.
This is serious calculator. Okay, we're not going to, 3,150 divided by 4,000 is that. Now, we're going to subtract from 1. And we're going to multiply by -1. So it's okay. And now we're going to multiply by 3,150. And then we're going to multiply by 0.2. And then we're going to add to 3,150. And we get a decimal. 3283 dot and then 7/8. So it's 3284. Now, I may have made a stupid mistake in the calculations, which would really hurt, but that's how you do it. Now, does this make sense? The first year, you get 3,150, and then you would expect it to sort of double, and it's close to doubling, but it's not quite doubling because each year doesn't go up by the same amount. So, that seems to be the way to do it, right? I mean, you could always make a stupid mistake in calculations. So, I'm not sure if it's worth us to look at the answer to see if we got it right.
Yeah.
But this is certainly how you do it. Okay, so now number...
Yeah.
Okay,
looks good.
Yeah, it looks good, right? All right.
Looks good. Okay.
The botanist would like to increase the number of plants that the environment can support so that the population species will increase more rapidly. Oh, if the botanist's goal is that the number of plants will increase from 3,000 to 3,360 next year, how many plants must the modified environment support? What? I don't quite understand.
Okay. Well, no, I think the deal here is you want the value of K. You want to solve for K such that the goal of next year 3360 equals what we have this year.
3,000.
This year is the original number. The starting number is 3,000.
No, you use the number from number 38.
Yeah. No. Yeah. You need the 3,000 from there.
Not here.
Yeah. You plug in the 3,000 three places. So you have so n next year is replaced by a constant 3360.
Right.
And this year is replaced by a constant 3,000.
Right.
And you solve for K to make the equation true.
Right. So it's a messier equation.
It's a messy algebra problem.
Right. So then we'll have to erase this. Again, I make no guarantee that the answer we have is absolutely correct. You should do your own calculations. I may have made a stupid mistake. But Seth, you're right. What I would have done, you swooped in and did it for me, which is great. But remember, I said I was lost. I would have. This is what happens when you're lost. Because frankly, when I read this, I didn't know what to do. I know that I go back to the original equation. When you're lost, you go back and read the original givens. And then I would have eventually seen that K is the number of plants the thing supports. That's what they're asking for. And then I would have realized, as Seth did, Seth reads better than I do, okay? Seth reads better than I do. So Seth realized quickly, Seth already knew, because frankly, I didn't really pay attention to this. When I read this, I didn't care less.
So the number of plants in that the environment supports, they tell you that in the formula, K is the number of plants that the environment supports.
Yeah, I know.
And that's what they're asking for.
Seth, but someone has to pay attention to that. And you think
you have to pay. Yeah, so you must pay attention to what the problem says.
Well, I certainly didn't. So I paid my price. But knowing that, I still would have gotten this right. I probably would have gotten this right because I would have gone back to the question. Because I would have said, well, what is this? And I would have read the question again, and then I would have paid more attention to this. Okay, we can't guarantee everyone reading the question will do it. Will read it as well as you.
You can't guarantee that everyone takes the SAT will get a great score.
Oh, Seth, come on. I would have gotten this question right if I reread the question, even though I had no idea what they were talking about at the beginning. So be a little forgiving there. Come on.
Not me.
Oh, yes, you are. Deep down, Seth.
Deep down,
Seth.
So all right. So let's see how you solve it.
I'm using a calculator, okay? And unfortunately, this is the last question of the test. And it is a doozy. I'm just slowly doing it. I'm just, as we're talking, I'm subtracting 3,000 on this side. So then, and this is 600. And I'm pulling some algebraic tricks, okay? I'm noticing that 360... then you divide both sides by 600. You want to get this term by itself, okay? Don't distribute. No. You want to solve for this term. That term, okay? So you divide by 600. So it's now I'm going to use a calculator again. So, it's fun. It's not really fun. Nothing's fun with this stuff. But I'm doing this while we're talking. It's because frankly, it's pretty boring to do this. Wait, calculus I froze. 6 seconds. Yeah, we have to just wait. So this is 0.6. 0.6 is equal to 1 minus 3,000 divided by K. So now you subtract 1. Thankfully, K is going to be, you're going to have 2 negatives, right? You subtract a 1 on this side, you get negative 0.4. is equal to negative 3,000 over k. We could do what Seth did. You just move the k. You just switch the k to the numerator. And k is equal to 3,000 divided by 4, 750. So k is 750. But let's do this a little slower, okay?
Okay, so let me do it.
You want to do this a little slower?
I'll do it a different way.
Wait. Well, let me finish. Let me finish doing this a little slower. Seth, please.
I'm going to do it slower, equivalent way.
Yeah, but let me finish this. Okay, so then if I would remember I'm into the cross multiplying stuff, which Seth is not into. You would do negative. I know it's slower, but it's more. But you always do the same thing every time. You don't have to think too much. You don't want to think. So you cross multiply. Negative 4k is equal to negative 3,000. Divide both sides by negative 0.4. Did I say 4? I meant negative 0.4. So this is equal to negative 3,000 divided by negative 0.4. Calculator says it's 750. Seth, go ahead.
Okay. Well, 3,000 is 4 symbols, and n is 1 symbol. So here's what I would do. I would rewrite the equation and use n for n sub next year. So I'd rewrite the equation n equals n plus 2/10 of n times 1 minus n over k. And we know n is known. We want to solve for k. Okay? And so I could divide both sides by n, right? And I get 1 equals 1 plus 2/10, just to show you what I'm doing, times 1. Okay, times 1 minus n over k. Right? We want to solve for k.
Wait, how are you getting that 1 in there? Oh, I see. Oh my God, look at me. Seth was drawing it. We didn't hide it. Yeah, okay.
Divide by n.
Wait.
Wait.
This
is
not n. This is 3360.
No.
There's a problem here. Next to
okay.
Seth, we got a problem
I'm
here. This is 3360, not n.
Okay. All right. So I made a mistake. Yeah, sorry about that.
This has not been your week.
All right. Well, too bad. Let's get rid of that. Too bad. Okay.
So nobody on the test is going to be redriving formulas. You're going to plug the numbers in.
Okay. All right. I'll plug the numbers in. Let me do it slowly. All right. I think it's better to plug the numbers in. Okay.
See, this is math. Seth changed his mind in the middle of the problem. This is exactly what you have to do.
Yeah.
If you realize you change your mind.
There we go. Yeah. 3360.
Okay. Let's have a redo.
Equals 3,000 plus 2/10 of 3,000 times 1 minus 3,000 over k. And I'm going to solve for k.
Sorry about that.
Okay. So I think so we could do the same thing. Divide everything through by 3,000 and get 3360 divided by 3,000 equals 1 plus 2/10 times 1 minus 3,000 over k.
Right.
And then, subtract 1 from both sides. If you want, use the calculator to simplify this.
There.
Or else simplify it by hand. I'll simplify it by hand.
No, don't simplify it by hand.
Okay, Seth, use the calculator.
3360.
While you're doing that, use the calculator, please, to calculate the left-hand side.
You want me to do? What? Yeah, but you have to tell me how. Because it's complicated.
3360 divided by 3,000.
Oh, yeah, I did that already. Yeah, I did that. 1.12.
Oh, so it's 1.12?
Yeah, 1.12.
Yeah, it looks right. So 1.12 equals this. So subtract 1 from both sides to get 0.12 equals 2/10 of 1 minus 3,000 over K. And notice if you could calculate what 1 minus 3,000 over K is, then you can calculate K. Well, so let's now solve for this thing.
Right.
So we divide both sides by 2/10.
And you get 0.6. 0.6.
Yeah, okay. So 0.6
0.6
equals 1 minus 3,000 divided by K.
Right.
Subtract 1 from both sides and get minus 0.4 equals minus 3,000 over K. Okay, then flip them around. K equals minus 3,000 divided by minus 4/10. Right. And so it's so this is cancel the minuses. We have 3,000 divided by 4/10, which is 3,000 times 10 quarters. Right. And it comes out the same.
No, I got it wrong. This is my time to get it wrong. Go back to the video. I said the answer was 750. Wrong. It's 7,500. I divided by 4 in my calculator, not 0.4.
Oh.
If you go back to my video, I erased everything. Okay. Thankfully, I erased everything because I don't want evidence of this. Okay? But I actually did it wrong. Wow. Okay. Oh my God! Look at that. Ooh, this is why it's so hard to get 100% on the SAT. I divided by goodness. Wow, Seth. Wow, look at that. And I was pretty confident I got that right. Ooh. So humiliating.
It also an answer 750. An answer 750 doesn't make sense in terms of the problem.
Right.
Because the problem is to increase the capacity of the environment in order to increase the number of plants the next year.
Right. Yeah.
And so increasing the capacity, so changing the capacity from what it was before.
Right.
Changing the capacity. Yeah. You want to make the capacity.
Right.
Bigger.
Yeah. So I really feel humiliated, but that's math. Yeah. Okay, I'm going to live.
Well. Okay.
But something to be lesson there is, did you notice what I was doing when I was solving that equation? Go back to the video. Did you notice what I was doing when I was scribbling here, doing all the stuff? Did you notice what I was doing?
You're making a big mess.
No, I was talking, and I was saying, this is boring. I'm just going to do this. I wasn't really paying attention to what I was doing. If you go back to the video, you'll see I was chatting with you. Oh, yeah, I can do this. No problem. This is easy. This is boring stuff. I wasn't paying attention. Oh, no. That's when it sneaks up on you. That's when you think everything's going well. When you got everything under control. Oh, yeah, no problem. I can do this. This is easy stuff. Oh, yeah, I can do this. That's when you get the problem.
That's it.
That's when you get the problem wrong. Wow. Good lesson to learn. I'm sure this happened to everyone already. But pay attention to what you're doing. Wow, look at that. Oh my goodness. Well, see how we make mistakes, but it's good for us to make mistakes because you see the mistakes we make. We're all in a team. Everyone watching this, hopefully, will think of us as a team. You learn from your mistakes. You learn from our mistakes. This way, you learn from more mistakes, which means you'll do better on the test. Okay? So. We really So, anything else about this? I mean,
let's do Throwback Thursday.
We could do the physics of this, but we're not going to. Okay, great. This is something in calculus. You do something like the growth equation or something. It's probably related to that. Okay, Throwback Thursday. You can sign off if you want. If you want. See you next week. Please email, like us, dislike us, give us comments. Okay, it's now time to go Throwback Thursday. This test is from 20 years ago. it's a fairly straightforward problem, but doesn't seem like they ask this type of question anymore. So here we go. How many of the prime factors of 30 are greater than 2? When I first read this, I said, but what about 1? Is 1 a prime factor? Is 1 a prime number? And then Seth reminded me saying, but it's greater than 2. See, I can't read. So I don't really, we don't have to worry about
in general,
yeah.
1 is not considered to be a factor of an integer.
So 1 is not prime?
1 is not considered to be a prime number, and it's not considered to be a factor of an integer.
Really? You sure?
Really?
No.
Yeah. No, it makes the math much cleaner. When this is put into a broader mathematical context, what we're talking about is a ring, and 1 is a special kind of element in a ring called a unit.
Oh, God.
Which is an element that has an inverse. It's a multiplicative inverse.
Oh, up here.
Yeah.
Up here. But wait a second. Okay.
And so the thing is, the unique factorization in ring theory is only up to units. That's the explanation.
Yeah, I know.
For what surprises you.
It's graduate school explanation.
They teach in high school. They teach in high school, so please remember it. It's taught in math. Math fact: 1 is not considered a prime number, and 1 is not considered one of the prime factors of an integer.
Okay, we're going to do this question, and then we're going to release everyone, and then I seriously have a question for my brother about this. So 1 is not prime. That's really all you have to know, okay? 1 is not prime. Anyway, it doesn't matter. So Seth, you want to take it from here?
Since I blew the last one? Just find the prime factors of 30. Okay. And the way you find the prime factors of anything is you factor like crazy until you're just left with prime factors. So, I don't know, 30. You could factor it as 2 times 15. 2 is prime, but you could factor the 15 as 3 times 5.
Okay.
And now we have 3 prime factors. 1, 2, 3. First, 1, 2, 3. Just count them up. How many of them are greater than 2? Well, 2 is not greater than 2. 3 is greater than 2. 5 is greater than 2. 1, 2. Count them up. 1, 2. The answer is 2.
The answer is 2. So a few people, I would say, what the decent percent of people, at least 10, 20% of the people will say 3 because they see greater than 2. They'll interpret it as greater than or equal to 2. Okay?
Well, they're wrong.
Yeah, I know they're wrong. I know
greater than means greater than.
I know.
That's what the scholastic aptitude means. You draw distinctions between greater than and greater than or equal.
Right, exactly, which means you have to read the question carefully. And this is particularly to be careful about this. Particularly when you're doing inequalities, you have to remember, is it this one or is it this one, right?
Yeah.
Which one holds?
Yeah.
Okay, so I guess we can release everyone but I do really have an interesting question, Seth, for you. I hope everyone enjoyed Throwback Thursday. You don't normally see this question on the modern tests. Okay, Seth, this is my question. And for those of you who are taking 11th grade math, maybe even pre-calc, there's that theorem that Seth knows how to prove. I have no idea how to do it. The one that says, like, if you have 3x to the 4th plus 4x cubed plus, maybe it's not a theorem, it's a thing, okay? And then 2x squared plus x plus 7, okay?
Yeah.
There's this thing, the rational roots theorem, which says that the rational roots, you're guaranteed, if there's a rational root, then you're guaranteed that it's going to be something like this P over Q, which are the factors of 7 and the factors of 3. So the possible rational roots are 7/3, 7 over 1, 1/3. Oh, these are plus and minus, okay? And then 1. Okay, this is called the rational roots theorem. Now, when you do the rational roots theorem, you have to consider all the factors of 3 and 7. So now what is this thing you said that 1 is not a factor of 3 and 7. In the rational roots theorem, you have to consider 1 as a factor of 3 and 7. You have to consider 1 as a factor of these numbers. Otherwise, you don't get the rational roots.
Wait. Well, so how do those numbers appear in the rational roots?
Wait, you don't remember? You don't remember the rational roots theorem?
No.
Whoa, look at you! You don't remember the rational roots theorem?
Nope.
Okay, should we go over the rational roots theorem?
Yeah.
Okay. Rational roots theorem says that if you have a polynomial like this, it has to be a polynomial with integer coefficients. Coefficients. If there is a rational root, now this is a 4th degree equation that may not be a rational root.
Yeah, we know.
But if there is a rational root, right?
Yeah.
Then it has to be in this set. It has to be in this set. Plus or minus, and then you take the factors of this one, the constant term 7, and the factors of 3, and you go like 7 times 1, 3 times 1, and you put all combinations of this. 7 over 1 is good. 7 over 3 is good. Oh, I really should do the plus minus. 7 over 1 is good.
Yeah, put all plus minus.
Minus 7 over 3 is possible. Plus minus 1/3. Plus minus 1 over 1.
Okay, I can explain that.
No, you don't have to explain it. You don't have to.
I can explain why you don't consider 1 to be a factor.
But 1 is a factor.
I will explain why.
Okay, I'll shut up.
Shut up. Here's the idea. You take the set of all the factors of 7.
Yeah.
And that set, there's you take the set of all, actually should be maybe it's divisors of 7, but divisors as opposed to factors. 1 is a divisor, but so instead of calling them factors, you call them divisors. But does the theorem say take all of the? I think it's So suppose the 7 were 14.
Yeah, then it would be 1, 7, 2, and
so what? So the possible numerators would be 1, 7, 2, or 14.
And 14, right?
Yeah. So what we're doing is taking. I think the principle is that instead of saying that you get that you form the set of possible roots, instead of saying that you form that set by taking all the factors of 14, you should say take all the divisors of 14.
Okay.
So example 14 is a divisor of 14. Well, of course, 14 is not a prime factor of 14.
So this book, Calculus Blitzer, just because this guy does it doesn't mean it's right. But he explicitly says factors. Say factors. Factors. See that?
Yeah.
So in other words, he did it. This guy did it. This guy may not be the theoretical mathematician that you are.
Yeah. But I think the bottom line takeaway is that you have to understand things in terms of what they are, and not in terms of just talking the language that people use to talk about them.
So in other words, you're saying for all practical purposes, for this application, you can use the word factor and you can get away with it. But if you're in this application,
so also in this application, what you're doing is using the word factor and divisor simultaneously.
Right. I wonder
synonymously.
Yeah.
Synonymously.
So if you have nothing else to do, sometime go on Google and see if you can ever find the rational roots theorem where they actually use the word divisor instead of factor. I bet
Oh,
for the at the 11th grade level, it doesn't matter.
yeah,
Yeah, yeah.
yeah,
Interesting, right?
yeah,
Interesting,
yeah,
right? The
yeah,
11th
yeah.
grade level, it doesn't matter. But if you're a
Rational root
fancy
theorem.
schmancy
Yeah,
Nobel Prize winning politician, a mathematician,
yeah.
you're not going to say that. You're going to have to say divisors, right?
Yeah. Well,
Wow.
I think, yeah. I think I can see the proof. The proof of it comes from, uh, it comes from,
It's okay. You don't. No
yeah.
one
Oh, maybe
cares.
I don't know.
No one.
Yeah.
No one. No
The
one really
proof. The
cares.
proof. Well, one thing too that I think one thing that is covered in elementary math, in high school math, is that the quotient, the constant coefficient,
Yeah.
divided by the high order coefficient, that the product of the roots is plus or minus that quotient.
Yeah, we talked about that, but isn't that
Yeah.
isn't that only for a quadratic?
For anything, any
Really?
polynomial.
Really? I
Yeah.
didn't know that.
Same reason.
Oh, okay. Wow.
Yeah.
Look at that.
Yeah, the
Look at
product
that.
of the root. Of course, when they're that makes sense only when all the roots exist in the field you're talking about, which is when you're
Right.
talking about complex.
Right. Right. Oh, I can sort of see how that works.
Yeah,
Right.
yeah,
Yeah. The product of the roots, right? Because you're
yeah.
saying very simply that. What is this? But this is. I
But
thought they had to wait. Okay, that's another question from. Oh, I see. So if you have x
yeah,
minus x minus something, and then you go this whole thing x to the fourth plus that. When
yeah.
x is equal to 0, these all cancel out. When x is equal to 0, these all cancel out. So you've got the product of all the roots. Has to equal that.
Yeah.
Okay,
Well, the way I like to think about it is that when it's factored, it looks like this.
Yeah, right.
And then let me finish.
Sorry.
And then you get the constant coefficient. When you expand this out, you get the constant coefficient in only one way, and that is to multiply minus a by minus b and minus c.
Right.
Where you multiply through, touching only the constants.
Right.
That's the only way you get a contribution to the constant coefficient.
Right.
And it's clearly the product of the minus a, minus b, minus c.
Right. We're a little schleppy with the plus and minus sign, but that's it. That's a
yeah. So it's the product of the roots times a minus 1 to the degree of the polynomial.
Right. Okay. Yeah.
Okay. And of course, you have to count the if there are multiple roots, you count them with multiplicity.
Right.
So x minus 1 squared. This has it only has one root, but that root appears with multiplicity too.
Yeah. Right. So you see this, right? This
which so it gets what, x squared,
you get a plus 1
minus 2x plus 1.
Right. Okay.
And plus 1 is 1 plus 1 is the first the root. Well, let's see, it's no plus 1. We're talking about 1 is the root, so we're talking about minus 1. But then if we're multiplying them with multiplicity,
then you have to square it.
You have the other copy of minus 1.
Right. Yeah. So then if you take the other 1 minus 1 cubed, then it's then you would get actually a junk minus 1.
Yeah.
Because this is minus 1 cubed.
Yeah, so it's minus R1 times minus R2.
Right. Yeah.
R1 is R2 is what? Yeah. Okay.
So we're really into
but I have to either think about or look up a proof of that
the rational roots theorem.
Rational roots theorem.
Yeah, look it up. Look it up. Okay, we go on a lot of tangents, but you know that's what's nice about YouTube. You can just turn us off whenever you feel like. So,
so the rational roots theorem means that you just try out a finite number of possibilities. The application of it is that it limits you to trying out a finite number of possibilities to find a rational root, and you're guaranteed to find it or them if there are any.
Right.
And then you could factor them all. You could then factor out all of the factor them all out. In other words, factor out x minus rational root.
That's right. Yeah.
And then you're left with a polynomial whose roots are all non-rationals, irrationals.
Right.
Yeah.
Right. Or complex.
Which means that
complex.
You'll get if you're doing this over the integers, over the rationals, and you get an irreducible polynomial. In other words, a polynomial you can't factor.
Right.
Okay.
Yeah. And then don't forget, if you have a cubic, you have a polynomial of odd degree, you're guaranteed at least one rational root.
No, the cubic means degree 3.
Degree 3, right? If you have a cubic or a fifth one, x to the 5th, x to the 7th, x to the 9th, you're guaranteed one rational root.
Oh.
Yeah. Because that's the only way across the axis, yeah. Yeah. If you have an odd, if you have x to the odd, you're guaranteed one rational root, aren't you?
No.
Yeah.
No. X cubed.
Yeah.
X cubed minus 2.
Yeah. X cubed minus 2. No,
yeah,
no, no. Real. Sorry, real. Wait, x cubed?
Oh, yeah, sure. Yeah, you're guaranteed to have a real root. Sure. That's different from a rational root.
Wait, x cubed?
Real. That's because, if you have a high x to an odd power plus lower order terms with the coefficient, I divided away the high order coefficients. X is a polynomial whose leading term is odd power.
Right.
Broadly speaking, the graph of a very, 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 very negative x.
Right.
The value is down here. And for very, very, very positive x, the value is up here, and somehow it goes somehow has to cross. As it goes from here to here, the curve goes. It has to cross the x-axis somewhere.
Oh, right. Oh, wow. So thanks for the insight, Seth. I always thought that. Oh, yeah.
That's why.
If you have an odd number, I thought the rational root theorem always applies, but technically it doesn't, because you have
it's a very different thing to talk about a rational root versus a real root.
Right. So it says if you have a rational root, then it's going to be this, and then it's going to be 2 over 1 or 1 over 2 if it's rational. But there's no rational root, so then the rational root theorem doesn't apply. Yeah. But on an 11th grade test, the teacher would be insane, absolutely insane, to give you a polynomial that doesn't have a rational root. That would never happen on an 11th grade exam. Right? The teacher would never do that.
What they might do is give you a polynomial, and one of the choices is there is no rational root.
Right.
So it's to say find. This is a logical math question that someone could ask. I'll say, put it this way. Find the set of rational roots for this equation. You grind through, and if you find no rational roots, then the answer is the empty set.
But this would never happen in a class. 3, 6, 18. Do you realize how many possible rational roots you have to test here? You have to test like a lot of rational roots.
The teacher use a computer.
Yeah, I know. But let's talk about exams. The teacher would never ask you to test these many and actually actually have none of them work. That would be totally insane. So, for all practical purposes, where they're going to test, if you have this question and you have to find rational roots, the teacher, one of the rational roots coming out of the rational roots term will work. Okay? Yeah. But that's interesting. Okay. That's interesting. 3 minus this. Yeah, this doesn't have any rational roots. Okay. I guess that's it. We both have to sort of go. Yeah. Anyway, today was nice. We hit a lot of stuff, and I made a humiliating mistake. Okay. So I guess we'll see you tomorrow, right?
Right, tomorrow.
Yeah, tomorrow. Okay. Have a great day, everyone. Bye-bye.
Bye-bye.